Today we're going to continue our four-part series on population growth and how it relates to first-order differential equations. Last time we talked about proportional growth, and now today we're going to kind of extend that model into logistic growth, and that's based off the idea that our environments aren't necessarily built to sustain an infinite number of people or of a species. So let's go ahead and take a look at our model in this case. When we're dealing with models like these, what it will be important to notice is that there is going to be some sort of carrying capacity, and that's what this k is equal to. There's a specific number that we can hold in our environment, and then past that number they won't be able to survive since there's not enough resources. And so you could think, based off this model, if my p starts to approach my k, as soon as I reach my k, then I'm going to have 1 minus 1, and I'm going to have the rate at which the population is changing with respect to time be equal to just 0. So we're not changing once we reach that carrying capacity. Okay, and today we're going to analyze the analytical solution to this differential equations model and then solve an example. Okay, so here's our first order linear separable differential equation where r and k are constants. I'm going to separate my variables here and then integrate to get these two integrals here. So on the right hand side I should have rt plus c, and on the left side, if I factor that k out from the denominator, since 1 over 1 over k is just k, to be k times the integral of dp over p times k minus p. Then I need to use a technique called partial fraction decomposition, and the whole idea behind that is that I want to split 1 over p times k minus p into two fractions so that I'll be able to integrate them a little bit easier. And then I'm putting linear constants on top of, well, constants on top of my linear terms, because when we do partial fraction decomposition, we want to go 1 degree down for in the numerator. Okay, and then from here I'm going to multiply both sides by that denominator on the left to get that 1 is equal to a times k minus p plus bp. If I let p be equal to k, then the a term will disappear, and I'll get that b is equal to 1 minus k after I arrive at the expression 1 is equal to bk. Plugging that in and then subtracting it over to the left-hand side leaves me with 1 minus p over k, and then if I combine them all into one fraction, I get k minus p over k is equal to a times k minus p. Then if I divide both sides by k minus p, I'll get that a is 1 over k as well. Coming back to our integrals and plugging those in, I'll get k times the integral of 1 over kp plus 1 over k times k minus p dt, or dp, is equal to rt plus c. Multiplying the k into the brackets leaves me with these two integrals here, which will become the natural logarithm of the absolute value of p minus the natural logarithm of the absolute value of k minus p is equal to rt plus c. If I combine them into one natural logarithm, I get the natural logarithm of p over k minus p is equal to rt plus c. Exponentiating both sides leaves me with p over k minus p is equal to e to the power of rt plus c. I use the idea that when we multiply exponents with like bases, we add the exponents to separate the c and bring it into the front. And then from here, I'm going to multiply both sides by k minus p, of course assuming that p is not equal to the carrying capacity, because again we wouldn't have a problem here if that was the case. Nothing would be changing. And then I'm going to isolate p by distributing those guys, adding p over to the left-hand side, and dividing by whatever I get when I factor the p out. And so it turns out that p is equal to k c e to the rt over 1 plus c e to the rt. And we're going to say that we're given some initial population at time 0 and come up with a more effective model with this. And so if I let this be the case, I get that p0 is equal to kc over 1 plus c, or that c is equal to p0 over k minus p0, and you can do this by using the same technique we used not too long ago to isolate for p when we had p over k minus p is equal to c e to the rt. Basically the idea is you're going to multiply both sides by 1 plus c, distribute the p naught, bring all the terms that have the c together onto one side, factor the c out, and divide by what you're left with. Now what we'll do is I'm going to put them all together. So I'm going to take that constant that I found and put it in everywhere where there was a c in our original solution. I'm going to combine the two fractions in the denominator to get this, k minus p0 plus b0 e to the rt over k minus p0. And then I'm going to multiply both the top and the bottom by k minus p0 to simplify the fraction a little bit. And this is going to be our logistic equation model here. P of t is equal to the carrying capacity multiplied by the initial population, exponential raised to the rate at which the population is growing with respect to time, times t over k minus p0 plus p0e to the rt. And this is going to be the general shape that our logistic equation takes on, right? Typically, we're going to start at some value for our initial population. We'll keep growing, we'll keep growing, we'll keep growing. We'll reach this sort of point of inflection, and we'll talk more about that later. When we reach that point of inflection, we're going to start leveling off, and so the population's growth rate is going to change with respect to time as we get closer and closer to that carrying capacity. Or if it so happens that we end up with more population than the environment can sustain in the area, the population will just begin to gradually decrease. And we'll discuss this more as well as we go through the example. All right, so suppose we have a population of deer in a specific environment, and that population doubles over the course of 3 years, with their population growing from 1,000 deer to 2,000 deer. And then we have some environmentalists evaluate their environment, and then they tell us that they can't sustain more than 5,000 deer. Now the question here is, how many deer will there be in the environment after 6 years? We've already gone over 3 years. How many will there be there in 6 years? Is it going to double again or not? Because this carrying capacity could impact that. We're going to have less and less resources available as the population grows. Okay, and then it says, what if the population rose to 6,000 deer? What would happen to the population at this point? And we'll talk about that as we go on as well. Okay, and so here's what we know. We have an initial population of about 1,000 deer. We know the carrying capacity to be equal to 5,000, so our environment can only sustain 5,000 deer maximum. And we know that there is some proportionality constant r, which will represent the rate at which the population of the deer is changing with respect to time. And we're going to have to compute that in this question using this formula, which I will discuss a little bit longer, well, not too long from now, where that's coming from. Okay, so now, yeah, where that is coming from is it's actually coming from the solution to our logistic equation. Again, normally why they would give you values like these in the question, because there are other means that you could use to go about finding proportionality constants using statistics or whatever. And so basically what we do is we say if our initial population doubles over some specific amount of time. So this formula is specific to when the population is going to double. Of course, you could just solve for r in the logistic equation solution right here to come up with a general formula for the rate at which the population is going to be growing based off the original information for when it's not just doubling. But I have this one formatted just for when the population is doubling. And that's going to be kind of where we get our model from, okay? And so this would be the differential equation that would correspond with our situation right here. Notice I've plugged in the initial population and the carrying capacity into that formula for our rate. And I'm not going to solve the logistic equation again here. I will just plug the values into the original solution that we found at the end of our first model, just to save time, with the initial condition that there were 1,000 deer in the environment initially. Okay, then that'll bring me here, because I'll take the carrying capacity, multiply it by the initial population. That's why I have 5 times 10 to the power of 6. Just put it into scientific notation. And then this rate that I have computed up at the top here is around 0.3269. Again, that's something that they would likely give you in the question if you were approaching something like this. Divided by 4,000, that's the difference between the carrying capacity and the initial population, plus 1,000 e raised to the 0.3269t. And this is modeled by this graph right here. Then to answer the question they gave us, after 6 years have passed, there will be around 3,200 deer. So it's not quite doubled again from 2,000 to 4,000, but we do have another 1,200 deer over the course of those next 3 years. Just a little bit more than what we had over the course of the first 3 years. Okay, now let's talk a little bit about points of inflection. So This is going to be something that occurs when we're dealing with logistic growth, is there's going to be some specific point in time when the population of the deer is going to start to level off, right? The rate at which the growth of the deer is going to change is going to have a specific point in time, and we can compute that using the second derivative. And so what you can do is you can find the second derivative of your logistic equation, set it equal to 0 to find your point of inflection, and then solve for t. In our case, it turns out that after 4.24 years, we will begin to level off to 5,000 deer in our solution here, and this is the formula for that. So if we were to take our information, plug it in here, then this would give us our answer here, and this is just derived from taking the second derivative of the logistic equation and then solving for t. Okay, in our case, on our graph, that appears to be around this point right here. You can see how it's kind of right in the middle there between when we change from concave up until concave down. Okay, and then the question also asked us what would happen if we somehow ended up with a population of 6,000 deer in our population. And okay, well, this would yield a different initial value problem. The rate at which the deer were changing is not going to be any different, but the initial population is going to be different, and so that's going to change most of these other factors out front in our logistic equation. And then it's going to create some sort of a graph like this one right here. So you can see that since the environment doesn't have enough materials to sustain 1,000 of those 6,000 deer, eventually 1,000 of them are going to die inevitably because there is not enough resources for them to live off of. And then we're just going to kind of level off at 5,000 again as time goes to infinity. Alrighty, hopefully that was helpful. If you have any questions, feel free to email me or send me a text message. I'm always open to questions. In the next video, we're going to go over what happens if there is some sort of minimum population as well as some carrying capacity that we need to have in order for our population to survive in an environment. And then after that, we're going to talk about predator-prey systems, which is something quite a bit more complicated, but I'm looking forward to speaking with you guys again. Have a great rest of your day.